All right, the material for today, the first and second sections are very closely related, so we're going to tie those two together. It starts out talking about perpendicular bisectors and then angle bisectors and putting them together into triangles. We're going to have, let's see, this chapter test I think is scheduled for next Thursday. So that's, the end of the quarter is Friday. So really there isn't much of any time to try and retake it. If there's an issue as far as passing or failing, we have to take care of that really quick at the end of the chapter. All right, let's go through vocabulary things. Okay, we're going to be using the word equidistant. What's it sound like that word means? Equidistant. Equal distances, that's exactly what it means. Equidistance is when a point is the same distance from two or more objects. The point is said to be equidistant from the objects. So when we use the word equidistant, we're going to have to say, like, Mrs. Frank is equidistant from the door and her desk. So you have to specify the locations that I'm the equal distance from. That's how you would use it in a sentence. Our perpendicular bisector theorem and its converse have the term equidistant in them. Now let's read through. Okay, so quit drawing. Let's read the theorem. Okay? If a point, you read it with me. If a point is on the perpendicular bisector of the segment, then it is equidistant from the endpoints of the segment. What's the hypothesis? Okay, so that's the picture. So the picture and the hypothesis, you're putting a point on the perpendicular bisector of a segment. So just like you did on your bell ringer, draw a segment, draw the line that makes its perpendicular bisector. Put the markings to indicate that's a perpendicular bisector. Then point X is a point on the perpendicular bisector of the segment. See how that fits what the hypothesis says? And they did write there just to clarify. XY is perpendicular to AB, YA and YB are the same, they're congruent. So what's the conclusion? Well, the theorem said that it is equidistant from the endpoints of the segment. What's it talking about? It. The point X in this picture. So X is the same distance from A and B. So the distance from X to A and the distance from X to B are the same. Equidistance. Those distances are equal. And I think we kind of lose sight of what these theorems are because you don't really even read through them. You just start drawing. Okay, converse is the second one. What's a converse? Opposite, meaning going like this. What's that mean? Okay, flipping. So what was the hypothesis is now is the conclusion. And what was the conclusion is now the hypothesis. Okay, let's read through the converse together. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So this time what you're drawing in the hypothesis is a point equidistant from the ends of a segment. So notice there's no perpendicular markings or anything. We're just showing that X is the same distance to A and B. Okay? Technically that line wouldn't have to be there at all, but it's there because we need it for the end of it. Okay? The conclusion is that point, is on the perpendicular bisector of the segment. So what is the perpendicular bisector's name in that picture? Line L or line XY, or maybe even just segment XY. There are different ways you could name it. So it's saying that although it's not marked, you can tell by this converse that that's a perpendicular bisector just because the distance from X to A and X to B are the same. That means it's on a perpendicular bisector. term locus is used in our books a few times, and so if you don't know what that word is, it's kind of confusing. So locus just means a set of points that satisfies a given condition. Locus is just a collection of points that follow a certain rule. So the perpendicular bisector of a segment can be defined as the locus of points in a plane that are equidistant from the endpoints of a segment. Okay, so let's explore that by constructing a perpendicular bisector. Okay, got a sheet of paper, or there's a little bit of room to the side there. Probably have to do kind of a small picture if you're doing it on your paper, but make a segment and construct, compass and straight edge, construct the perpendicular bisector. We've done that before. Construct the perpendicular bisector. Perpendicular bisector. I call it the football construction. It has two crossing arcs. You have to cross twice. Draw an accurate perpendicular bisector. Doing the same arc from both ends, right? I know this is without a compass, but you got this and this. Drawing that. Okay, what you just created is a perpendicular bisector. Those two segments are the same. Now it says, consider a point on the perpendicular bisector. Let's even just put a point where those two arcs cross. Now think about your construction. What would the distance from, I'll call this x, from x to A and x to B, we're supposed to compare those two distances. X to A, is it the same distance from x to A and x to B? If you really think about your construction, if I put it right where the arc was, my compass setting when I went from A and when I went from B didn't change. So that would be, if you think about your construction, the very same length. But if I go a little bit lower, let's put a point Y right there. Is it going to be the same distance from Y to A and Y to B? I'll try it. Put a point lower. You can even compare with your compass, I guess. Is the distance from Y to A the same as Y to B? Are those two the same? Same amount? Is Y equidistant from the endpoints of that segment? Should be, yes. If I went further down, should be the same thing. Further down. So this locus of points, all of these points are equidistant from A and B. That's kind of the description there using the term locus. Okay, so if you have that picture in mind, here's a simple problem. Find each measure. Find the length of MN. What's the length of MN? Well, notice in the picture, This line NP is a perpendicular, and it goes through the midpoint, so it bisects. So the theorem said any point that's on there, like N, is equidistant from the ends, M and L. So N to M is the same length as N to L. So how long is NM? 2.6. You're just using that perpendicular bisector theorem. Find the length of BC. You need to first figure out if there's a perpendicular bisector. I see the perpendicular, you probably do too, but there's no tick marks to show that it's a bisector, right? Doesn't tell me that BD and DC are the same. But, right, the 38 and the 38. So this is the converse. This point A is equidistant from each end. So that converse said A is on the perpendicular bisector. So if it's already marked that it's perpendicular, then by that converse we would know it bisects. So DB and DC would be the same length. So what is BC's length? It's not 12, it's 24. Right? Because it would be 12 plus another 12. This part is 12, this part is 12, so 24 total. So that one used the converse, the equidistant idea, to know that it bisects. How about find the length of TU? Are we using the perpendicular bisector theorem or the converse of the perpendicular bisector theorem? Which hypothesis do we have? Do we have a perpendicular bisector? Jacob's saying yes. I agree with Jacob. He's the only one that was answering that. Okay. So if U is on that perpendicular bisector, use equidistant from T and V. How would you do the problem with this? Correct. And do the calculation, who was fast? What do you got? Nobody?
X equals 6.
6 or negative 6? I don't think I'm getting either one. 6.5. 6.5. So then TU, substitute in 3 times 6.5 plus 9, so 28. Like some simple problems. Now let's use an idea that we did previously. Remember in chapter 3, we were dealing with perpendicular bisectors and writing equations? It's coming back. I want to do that again. Write the equation for the perpendicular bisector of the segment that goes through 4, 6 and negative 2, 2. What point does the perpendicular bisector have to go through? The midpoint. Okay, find the midpoint of those. Find the midpoint. I don't know if it's just based on your notes right there. Equation of the perpendicular bisector. What else do we need to have to write the equation of the line? We've got a point. We need slope. Okay, so we can find the slope of segment AB. Are we going to use the same slope for the perpendicular bisector? No, how do we change it, Zach? Opposite, sine, and reciprocal. Okay, so find the slope of AB, and then we'll fix it up. slope. Midpoint and the slope before we can write the equation. What's the slope of AB to start with, Kate? -3/2 originally? So, no? That's when, after you changed it, so originally it was positive 2/3? Okay, AB had a positive 2/3 slope, but we have to change it for the perpendicular bisector. So we change it to use -3/2, like she said. Okay, midpoint was 1/4. The slope that we want to use is -3/2, so how do we write the equation of the line? Let's use point slope form. Y minus 1 equals -3/2, parenthesis, minus the x part. 1. Did I say the wrong thing? Okay, I'm sorry. Did I say the wrong thing to start with? So y minus 4 is what I should have said. Y minus 4 equals -3/2, parenthesis, x minus 1, parenthesis. Okay, sorry. And then I distributed and put it into slope intercept. Okay. There are a couple problems of perpendicular bisector equations on this assignment for you to remember how to do. So there's a reminder. Okay, now since a triangle has 3 sides, there's going to be 3 perpendicular bisectors on a triangle. And when you draw or construct them, you'll find that they have an interesting property. So I think just on a separate sheet of paper, I didn't give you a big blank space, but on a separate sheet of paper, just grab some. Let's have you make, with your straight edge, a large scalene acute triangle. Scalene acute. And then you're going to need your tools. Okay, you need to create the perpendicular bisector of every side. And you can choose to construct it or grab your ruler and protractor and measure to create it. But you need the perpendicular bisector of each side. If you were good with the construction, maybe you want to just construct it. Use points A and B, make its perpendicular bisector. And then maybe turn your paper. Do the perpendicular bisector of every side. How many think they're going to try constructing? Some of you are just measuring. Right. Majority appear to be just measuring. So measure and mark where the midpoint is. If you're constructing, go ahead. Measured and just marked where I think the midpoint is on each side. Now what else would I have to do though? Got to make sure it makes a 90-degree angle when I draw it. So I'm going to use my protractor. You decide how you think using it would work best for you. But I'm going to lay the 90 there. On mine, I can draw along the bottom of it. I don't know if you can do the same on yours easily or not. Measure where a 90 is and you can probably lay your protractor along that side somehow there. And get the 90 angle lined up. Draw the perpendicular bisector. How's yours coming, Connor? I think the constructing actually might be easier to do. You are bisecting the that way. You need to be bisecting the side. Do this one just starting. That'll come handy for our next part of our lesson. If you're doing the constructions, you're going to have arcs to get the perpendicular bisector of every side. Do that on every side of the triangle. It says that it has an interesting property. It's got to go through the midpoint and it's got to be perpendicular. What's the interesting property? The interesting property is we should all meet at one point. The construction looks like it probably was easier to do. All right, when those three lines all come together to make one point, there's a special term for that. Yeah. These lines are all concurrent, and this point where they all meet is the point of concurrency. Now this chapter, there's going to be 4 different points of concurrency. So you're going to have to learn that this one is where the what meet. What did we just draw? Three perpendicular bisectors meet to create what's called the circumcenter. Circumcenter is where the 3 perpendicular bisectors meet. Circumcenters can be inside the triangle like I did, so mine kind of looked like this first one. This is a perpendicular bisector, this one's a perpendicular bisector, this one's a perpendicular bisector. They all met at point P, the point of concurrency, the circumcenter. If you started with an obtuse triangle, when you do the perpendicular bisector of each side, perpendicular bisector, notice that they meet outside the triangle. And if it's a right triangle, this one's perpendicular there, bisecting. Where do they all meet?
The
Hypotenuse, and actually the midpoint of the hypotenuse. Now what's special about these? The theorem is going to tell me in just a little bit, but I want you to try it. If you think you have a pretty good picture of a perpendicular, or of where they all meet, put your compass point right on that location. Put the point right there, and open your compass to one of the corners, like point C, but it should also hit point B and point A. It should be the same distance to all of those corners. Mine's off just a little bit. Notice how I could draw a circle and it touches every vertex? that circumcenter is the same distance from every vertex of the circle or of the triangle. Did that work for anybody? Connor, did your construction work well? Not really. Anyone's working well? Somebody got it to work real well? Okay. All right, if that really is a circumcenter, it's the same distance, even if it's obtuse, it would be the same distance from P to each of these corners of the triangle. So that's what our theorem says. And the term right at the bottom, I drew the circle around it like I did on the board. Okay. The circle that goes around it is called a circumscribed circle. I might add a picture at the bottom there before we turn the page. A circumscribed circle goes around the triangle or polygon, touching all vertices. You create it by using a circumcenter and the circle that goes around it. Circumscribed circle. So here's the theorem finally. Circumcenter theorem. The circumcenter of the triangle is equidistant. What's that term mean? Equal distances. It's equidistant from the vertices of the triangle. So I gave you the picture and had you write the words here because I thought the picture was a little bit hard to do accurately. You might put a note by that one. What's the circumcenter made out of? It's the 3 perpendicular bisectors. Picture, I know I've marked all that, but it might help to write those words. 3 perpendicular bisectors make the circumcenter. It's equidistant from the vertices of the triangle. Why is that? Well, it's really a perpendicular bisector theorem 3 times. If P is a point on every perpendicular bisector, so it's equidistant from the ends of the segments. So it's the same distance to the end of every side, no matter which direction you're looking at it. In this chapter, there's going to be a lot of pictures that look about the same. The next one is going to have angle bisectors. What I do is concentrate on that common point, that point of concurrency, and then look to see I've got perpendicular, and they've marked that it bisects, so those red things are perpendicular bisectors. So then I've got to know the theorem. It's the same distance to every corner. PC, PB, PA are all the same length. If you can visualize that circle that goes around it, that kind of helps you figure out which ones are brain drawing. It looks like you're done with your notes. So here's an example problem. Okay, it says DG, EG, and FG are perpendicular bisectors. So notice not everything's in the picture marked. Perpendicular bisector, perpendicular bisector, perpendicular bisector. So G is the circumcenter. The theorem just said the circumcenter is equidistant from the vertices of the triangle. So GB, GA, GC are all the same length. So how long is GC? 13.4 because GB was 13.4. So if you can pick out the right measurements in the picture, the answer is not difficult to come up with. Is GE the same length as GD and GF? No. It doesn't say that that point is equidistant from the sides. It says it's equidistant from the vertices. Find GM. This point Z is the circumcenter. Not a lot of markings in this picture. Circumcenter, equidistant from the vertices. What's GM? I'm think it's 14.5? Can you justify that? Can you justify it? Or is it just a guess? What's this point called? Okay. This point is where the three perpendicular bisectors meet. So evidently ZM is a perpendicular bisector. So that's why we would get 14.5. Again, you have to look at the picture and look at what measurements are there. Think about what the directions are telling you. Find JZ. It says Z again is a circumcenter. Is it 19.9? Yes. ZG and ZJ would be the same length. Okay, now let's switch to angle bisectors. Okay, what's an angle bisector do? Okay, got your protractor. Maybe we can measure this one pretty easy. Okay, kind of in that bottom space there on your paper, draw yourself an angle. How about just an acute angle? Won't make it too complex. Draw an acute angle, and then grab your protractor and bisect it. If you really want to, go ahead and use it with your compass if you remember how to bisect an angle. Bisect an angle. Either measure and mark it or construct it. Cut it in half. You got an angle bisector? Okay, bisect the angle now. Cut it in half. Cut that angle in half. Okay, now the theorem, let's see what it's going to say. The theorem says that if a point is on the bisector of the angle, it's equidistant from the sides of the angle. Let's try that on your picture before we go to writing down things about the theorem. Okay, so pick a point on your angle bisector, and we need to measure how far is it from each side. When you measure, you have to measure at a right angle. Remember talking about that? Distance is along a perpendicular. So with your protractor, mark where it's really perpendicular. You can see through your protractor better than I can. And then on this side, slide it till it points right at that point. Where those are 90 degrees. Then measure. How long is that distance? How long is the other distance? The theorem's saying those distances are going to be the same. But you have to make sure you're measuring at a 90-degree angle. Otherwise, the distances would not be the same. Tricky to get the 90 measure to the side of the front, side of the angle. sense out of it? Okay. Let's go ahead to the theorems. It says if a point is on the bisector of the angle, then it's equidistant from the sides. So this point C that's here is the same distance to the bottom side of the angle and that other side of the angle. But the tricky part on this one is when you measure to the sides, you have to form a 90-degree angle. Not where the point is, but at the side of the angle. That's where the 90 is. From point C to the ray. So the theorem says if that's on an angle bisector, AC and BC will be the same. The converse, if you know those lengths are the same, then you'll be able to justify that that ray is an angle bisector. So you either start knowing that it's an angle bisector or conclude that it's an angle bisector, depending which theorem you're using. So equidistant, but equidistant from the sides instead of the vertices. So it's a little bit different thing. Did that work well on anybody's picture? That it did? You did get those lengths to be the same? And some did. It's a little bit hard to do that accurately. Done with the notes? Okay. Again, can use the locus of points. This is a picture that would relate to either the angle bisector theorem or its converse. Now in this one, we do know that the angle's bisected, so we're using the original theorem. The original theorem said a point that's on that angle bisector is equidistant from the sides. So what's the length of BC? 7.2, just like DC. It's the same distance to each side. This one, we don't have the angle bisector, but notice what we have, H. If you go perpendicular to this side or perpendicular to the other side, those two lengths are the same, so this is the converse. If H is equidistant from the sides, then we know this is an angle bisector. So we're supposed to find angle EFH. We're supposed to find this angle, and we're given that EFG is 50. So 25, we're cutting 50 in half. Correct. Notice M is the same distance to the L side and the J side. So that means it's on an angle bisector, which would mean these two are the same. So 3A plus 20 equals 2A plus 26 to solve the problem. Now this one says find an angle measure in the end. So once we find A, we can't stop. A is 6. So what angle are we supposed to find? MLK, so just one of those small ones. So 2 times 6 plus 26 to finish the problem. If you put all of the angle bisectors together, you'll create another center point, but it's not a circumcenter, it's an incenter. Okay? So let's try and draw some incenters. I don't think we have time to really measure it all. Okay, in that acute triangle, you have your protractor, so maybe you can do some fairly good pictures. When you bisect every angle, cut that one in half, cut this one in half, cut the top one in half, they will always meet inside the triangle. Incenters are always in the triangle. Circumcenters could have been outside or could have been right on the triangle, but incenters are always inside because they're angle bisectors. Again, bisect the angles. So put your markings. What you're doing is bisecting the angles. Makes an incenter. Even on the right triangle, bisect the angles. Now we create an incenter. There is a circle you can draw with this one. It doesn't go on the outside, it goes on the inside. So I think the next term in your notes is an inscribed circle. That circle, I'll draw it on a few of these, that circle actually goes inside. If I had my compass, it would be better. But there's a circle that can be drawn inside. So when you go from point P, it's not the same distance to every corner. It's the same distance to each side of the triangle. You measure those perpendicular distances, those would all be the same. Ready to see an incenter or inscribed circle? Put your markings on those angles so you know that you were drawing angle bisectors. Maybe even put the word angle bisectors by those. The circle goes on the inside. I showed you that on some. So that's, I clicked past it again. All right, there it's done. Okay, the inscribed circle goes on the inside. So what's the theorem tell us? Looking at the diagram of the theorem, what's going to be the same length from P to the side? So P to X, P to Z, and P to Y are all the same. So the wording, the incenter of the triangle is equidistant from the sides of the triangle. How do you know it's an incenter? Well, either the directions will tell you it's an incenter, or what's an incenter made up of? The three angle bisectors. I'll give you a hint how I have to think about it to remember. Incenter starts with a vowel. Angle bisector starts with a vowel. Circumcenter starts with a consonant. Perpendicular bisector starts with a consonant. So I kind of pair up in my mind the things with consonants and vowels. That'll be true tomorrow also. I can go through a couple more of these. So that's the way I can remember it partially, is the vowels and the consonants. They fit together. So what's the picture going to look like on this part of the assignment? And if you didn't get the wording completely, you might have to finish up from your textbook. All right, I'll flip back to this, but I'm going to have to go to another example. So sorry if you're a little bit behind, I'll come back. Okay, on some of these pictures, I don't know why, they don't always put all three angle bisectors. They just put two of them. For some reason, they don't draw this last one in. Okay? But this point, it says, or I guess it says those are angle bisectors. So this point is the incenter. Okay, what's the distance from P to MN? Distance from P to MN. So what's the distance to this side? Same as the distance to any side, so 5. That distance is the same. And then they'll have you do one where you try and find an angle major. Okay. We said that this was an angle bisector. So if this angle's 50, what's this one? 50. I'm trying to find angle MPN, this angle. Well, if I could find the whole corner, I could take half of it. We can find the whole corner. What do the 3 angles in a triangle have to total? 180. Now what triangle am I looking at? The big one. This angle is 20. This angle is 100. So that's 120. So that leaves, I guess, 180 minus 120, 160. 60 is this whole angle. So M, or PMN is half of 60, so 30 degrees. 30 degrees there, 30 degrees there. Like I said, for those pictures, for some reason, they didn't put all 3 angle bisectors in the diagram. All right, looks like that's all we have time for today, but let's squeeze in an assignment. Yeah. Okay. There are 2 sections, but I'm focusing more on the second section. So the first one only has a few problems. Second one, a lot of single problems I pulled out, and I did not get this into e-backpack yet. So make sure you get it on the board. Some fairly quick problems if you know what you're looking at in the picture. So yeah, either get that written down or snap it real quick so that you know what the problems are for tonight. I don't think you have to draw anything. I think it's mostly calculated. I guess if you run into that, you'll have to do it quick. Throw it from your desk. I think what's hard in this chapter is there's a lot of diagrams that look the same. So you'll have to focus on each diagram and see what's in there.